In this lecture, I'm going to talk about graphs, not just graphs of functions, but graphs of curves in general. And the three things that I want to talk about are intercepts, symmetry, and intersection. Those are the three topics. We'll only talk a little bit about intersections. I'm going to just hit this kind of lightly because I think that we have a lot of technology that will allow us to sketch, actually not sketch graphs, but allow us to actually graph things very accurately and with a lot of precision. I think it's still worthwhile to be able to kind of sketch the graph so you kind of have an idea of how a function behaves. But in terms of getting into detailed graphs, we're probably better off using technology for that. Nonetheless, in calculus, the ability to find intercepts or find points where a graph crosses the x or y axis is important. Understanding something about symmetry and especially being able to find intersections of two graphs is important. So I just want to review those topics in this lecture. So just in terms of intercepts, just remind you what an intercept is. So if we are in the xy plane, let's say we have a line like this, then the intercepts are where it crosses the x and the y-axis. So this would be the y-intercept, and this would be the x-intercept. We could have more than one intercept. So for example, we might have something that goes like this. If it's a curve, here we have 3 x-intercepts, and right just below this there would be our y-intercept. Another example would be something like sine x. So we have this sine wave that continues forever. Whoops, this is actually cosine, right? Because we're up here, not starting at the origin, but either way, both sine and cosine have an infinite number of x-intercepts because these waves kind of continue in both directions on the x-axis, but there's only one y-intercept. It's also possible, if I were to draw something like just a parabola like this, to have no x-intercepts, but you would still have a y-intercept here. So anyways, there's lots of possibilities here, but what an intercept is where the graph crosses either the y-intercept or the y-axis for the y-intercept, the x-axis for the x-intercept. So now I want to just give a quick example of how we would find the x-intercepts, actually not just the x-intercepts, the y and x-intercepts algebraically. So if I had a function x squared minus 6x minus 7. All right. Now what I want to point out here, the connection between the graphical and the algebraic. So notice along the y-axis, if I want to find first the y-intercept, then notice along the y-axis, the value of x is 0. So if I put in 0 for x here, I should find out where this graph crosses the y-axis. So I just find f of 0. That's 0 squared minus 6 times 0 minus 7. So that's just negative 7. So that tells me that the point 0, negative 7 is on this graph. So let's just go down here, call that 0, negative 7, and that is my y-intercept. Now, likewise, along the x-axis, the value of y is 0. And we can think of f as being another name for y. Right, this is our function notation, but it really just gives us the y values. We put in a value for x for the independent variable, and we get the dependent variable, whether you want to call it y or f of x, is what we get out. So what we're saying is to find out when it crosses the x-axis, we need to find out when y equals 0. So since y equals this whole thing, we set that equal to 0, x squared minus 6x minus 7, and we want to find the values of x that make this expression equal to 0, because at that point then y will be 0. So in this case, the easiest is just to factor it. All right, this factors nicely. I need two numbers that when multiplied give me negative 7, but when added give me negative 6. So minus 7 and plus 1 fit the bill, right? So you can FOIL this out and check that, but notice here that I have, if I put in a number for x here, I have two numbers that are multiplied, and I want to know when their product equals 0. Well, that will be true either when one of them equals 0 or when the other one equals 0. And you can basically just by inspection see that this is going to happen when x equals 7, this is going to happen when x equals -1. So put in -1 here, and then maybe go out to 7 here. And so here is, and again, notice this is actually 7, 0. It's the point 7, 0. This is the point -1, 0. So I could actually use this to graph the, let me just use another color for that, just to graph this. It comes down, goes through here, and then it comes back up. All right. So I can use, I also know that it opens upward because the coefficient here of x squared, well, we don't usually write it, I mean, it's implied to be 1, but since it's positive, we know our parabola opens upward. The other thing I just want to quickly review is in this case, it factored nicely into two integers or whole numbers. What happens when it doesn't? Well, or what happens if you're just not very good at factoring? Well, you can always use the quadratic formula. I'm actually going to go to the next page because this will take a little bit of space. So if you remember the quadratic formula, it tells us that the x-intercepts occur at negative b plus or minus the square root of b squared minus 4ac over 2a. And we're interested in finding the x-intercepts. We're just going to use the same function. We can just see how, kind of verify that what we found before. What we found before was that the x-intercepts were at 7, 0 and at -1, 0. So it'd be nice to see if we can get the same out of here. So notice then a, we already said a equals 1. That's the coefficient, right? So this is true for ax squared plus bx plus c. So any quadratic of that form, we can put in the coefficients in order to find the x-intercepts, all right? So in this case, a equals 1, b equals -6, and c equals -7. So let's go ahead and plug that in. Negative of -6 is +6 plus or minus the square root of -6 squared, which is 36, minus 4 times 1 times -7 all over 2a. A is 1, so that's just 2. Now if you were to simplify this, you would find that this is 6 plus or minus the square root of 64 over 2, which is 6 plus or minus 8 over 2. That's going to give us two roots, right? One of them is going to be 6 plus 8 over 2, which actually does give us our 7, and then the other one is going to be 6 minus 8 over 2, and that will give us our -1. All right? In general, if b squared minus 4ac is positive, we end up with two x-intercepts. So that's what we found here. We see it looks like this, crosses the x-axis in two places. If b squared minus 4ac equals 0, then you end up with one x-intercept. Graphically, that would look something like this. Kind of comes down, touches in one place, it comes back up, you know, could come up, go back down, but there's only one here, right? Notice that if it were 0, that this would be 0, so it would be plus or minus 0, which doesn't, you know, in other words, you would just end up with 1. Right? It would just be the negative b over 2a because this whole part would be 0. And then finally, b squared minus 4ac being negative, we have 0 x-intercepts. So we would have something like this that doesn't cross the x-axis at all. Okay, so the other thing that I want to mention is, although we can do this with the quadratic formula or factoring, we can also find them using technology as well, whether it be a graphing calculator or something like GeoGebra. It's not hard to find these, especially when they're not integers. But I think it's also worth being able to do this by hand. So that's why I'm showing that. I just wanted to mention technology sometimes can be used for that purpose as well. All right, then symmetry. I want to talk just a little bit about symmetry. Three types of symmetry: y-axis symmetry, x-axis symmetry, and symmetry with the origin. All right, so the y-axis symmetry, I think it's easiest maybe just to give an example. So if I have something like x squared minus 2. All right, so we know that our y-intercept is at -2, and it comes down, and it comes back up. So the symmetry is the idea that if you take half of this and reflect it across the y-axis, it looks exactly like a mirror reflection on the other side. All right. So, for example, if I wanted to put in the value of, 3 here, notice if I put in 3 here, 3 squared minus 2 is 7. So that would put me, like up here. That would be 3, 7. Likewise, -3 would also result in 7, right? Because -3 squared is 9. So -3 is 7. And so this is, if we think about, so graphically we just see this reflection, but in terms of looking at individual points, we see that so with the y-axis symmetry, if xy is on the graph, then so is -xy. So again, with this example, if I put in 3, I get 7, but if I put in -3, I get the same y value out. So for any x value, the y value associated with it, if it's positive, then the negative has the same y value. That's basically what it says. Now, this only shows us for one particular example, right, for x equals 3. If we want to show it in general, then what we want to do is we want to put in, so we have here that y equals x squared minus 2. What we need to show is that if I put in a negative x, I still get the same y value, right? Well, if I put in, well, I don't want to say equals just yet. So let's say if I put in negative x and I square it and I subtract 2, well, negative x squared is just negative x times negative x, right? Well, that's x squared, right? Because the negatives cancel or make a positive. But that's the same y that I started with, right? So if I put in negative x, I get back the same y. So this is how we would test in general. This tells us for any x that I could put in, it's going to have this property where if I put in the positive and then put in the same number that's negative, I'll get back the same y value. Okay, so I wanted to go in a little more detail this one because these are very similar. So I'll go through those maybe a little bit more quickly. So for example, x-axis symmetry. Here's a quick example. Something like this. All right, so this could be the curve x equals y squared. So out here at, I don't know, let's call it 4, I could have y could be 2 at this point, or down here, y could be -2, right? If I put in 2 for y, I get 4. If I put in -2 for y, I get 4. So you see this, now the mirror reflection, the top half is mirrored by the bottom half across the line, or across the x-axis. All right, so you have that reflection symmetry going on across the x-axis. Here, this rule, you could see the difference is going to be if xy is on the graph, then so is x negative y. All right. So like in the same way, we see it already here, right? We have this point right here is 4, 2, and this point is 4, -2, right? So if 4, 2 is on there, then the same x value with a negative y is also on there. Again, this is a specific example. The way we would show it in general is we would replace y in this equation with negative y. And then we would square that. We would get y squared, which is equal to x. So whether I put in y or negative y, both of them are equal to x. All right, finally, I want to just talk about origin symmetry. So with the origin symmetry, we have something, let me center my paper here a little bit better. So I'll give you an example of a graph that has origin symmetry. So I can draw it like this, and it's symmetric about the origin if you have the same thing coming down this way. All right, so this could be the graph of x cubed. All right, so graphically one way to think about this is, and I'll kind of draw this in with another color. First, I could reflect this over the y-axis, right? And I would get something like this. All right, and then I could reflect it over the x-axis. So I take this and flip it over the x-axis, and then I would come down here and I would get this part right here. So you can kind of think of it as a reflection over the y-axis, then over the x-axis. I could just as well have reflected over the x and then the y to get down here. All right. Another way to think of it, if this is our curve, is that if I turn my paper around, let's cover that part up, you see I get the same graph. If I turn it upside down, I get the same graph. Is another way of thinking of this origin about the symmetry. All right. In terms of algebraically, so this is y equals x cubed. So if I put in the point, I don't know, say this is 2, then up here, that would be 2 cubed, or 8. Then over on this side, if I put in -2, I'd come down here, and I would get the point -2, -8, because -2 cubed is -8. So here, if xy is on the graph, then so is -x, -y. Again, the way to test that, if we want to test to see if this has symmetry with respect to the origin, then I know that y equals x cubed. So if I put in -x and I cube that, I get -x cubed. But notice if y equals x cubed, then -x cubed is -y. So I put in -x, I get out -y. That shows that for any value of x that I could put in, I would have this property. Okay, last part is on intersections. If I want to find, how do I find the intersection of two graphs? So let's see, I have an example. Let's say y equals x to the 4th minus 2, x squared plus 1, and y equals 1 minus x squared. So the graph of this looks something like, so this one, x to the 4th plus minus 2x squared plus 1, looks something like it comes down, and it touches, it goes up, comes down, comes back up. So notice, well, it's not a great sketch, but if I did it right, we would have symmetry with the y-axis here. All right, and then a different, so 1 minus x squared, that is going to look something like this. All right, so notice, just if you look at the graph, it looks like I have 3 intersection points, and I want to find those intersections. All right, so notice that what I want to do ultimately here is I want to find these points where the two graphs have the same x and y value. So if I know that they have the same y value, then this y must equal this y. So what I'm going to do is I'm going to take the x to the 4th minus 2x squared plus 1, and I'm going to set it equal to 1 minus x squared, since I know the y values are the same. And then this will allow me to see which x values make the y values the same. All right, so let's get everything over on the left side. So I would subtract 1 and I would add x squared here. So let me subtract 1 and add x squared here. So over on the right hand side I get 0. I have x to the 4th, and then minus 2x squared plus x squared just gives me a minus x squared, and the 1 minus 1 gives me 0. So I'm left with solving this equation. I can factor out an x squared. That leaves me with an x squared minus 1 equals 0. So once again, I set x squared. Either one of these being equal to 0 makes this true, so I set x squared equal to 0. That's only true when x equals 0. Likewise, I can set x squared minus 1 equal to 0, or x squared equals 1. That will happen when x equals plus or minus 1. All right, so you can see right here that looks about right. We have 1 at 0, and we have these at plus and minus 1. These are just the x values of the intersections, though, right? We still need to actually find the y value. We can plug in either of them since these points are on both of these graphs. So this one's easier to use, right? So one intersection, if I put in 0 here, so one intersection point, this one right here is 0, 1, because if I put in 0, I get 1. And then if I put in -1 to this right here, I get -1, 0. And if I put in positive 1, I get this point over here, which is 1, 0. So here are my 3 points of intersection. So the general idea algebraically, if you want to find intersections, set them equal and solve the resulting equation. Again, this also can be done with the graphing calculator or with GeoGebra, but it's still worth knowing how to do by hand as well.